let's talk about real numbers. Like, what does that even mean? What makes a number real? Interesting question. There's a little bit of a debate about numbers. The debate is about whether numbers are invented or discovered. What I mean is, some people believe that numbers are invented, that they are something that as humans we created, and we use them to, understand things. Other people believe that numbers sort of exist out there in nature, and we've discovered them. Personally, I'm a little bit more on the invention side, right? I kind of feel like numbers are something that people have come up with in order for us to try and describe things in the world, describe different situations that come up, and to help us think clearly about situations that we encounter. But maybe I'm wrong. I kind of think of it like a game of chess, Chess is clearly something that humans have invented because, why is the chessboard the shape it is, 8 by 8? Well, that's kind of arbitrary. Somebody somewhere in the past history, they made that decision. Why do the pieces move the way they move? Why does the game end when the king dies? These are all decisions that we came up with, and they could have been different, but they are what they are. And once we've defined sort of the rules and properties about how everything works, you can sit down and play a game of chess with somebody else. But when you do that, that's when the discovery process begins. Because now, given that set of rules, you start to discover deeper levels of strategy. You start to discover what moves are good, what moves are bad. Patterns tend to emerge by themselves from the rules of the game, from these arbitrary rules that we created. And I think that numbers and math are kind of like that. Like, we invented them, but once we did, we can start to discover many important properties that emerge from numbers and patterns that come out, and discover meaning in how we use numbers. And I think that's sort of how math works overall. So I'm going to talk about real numbers today, but I kind of want to start from the beginning, from more simple types of numbers, and show you how when we encounter limits to what we understand numbers to be, we figure out a way to break out of these limits and redefine numbers or think about numbers in a new way. So let's imagine you go back in time 10, 20,000 years, and you're going to go fishing with your buddies, and you have a little contest, a fishing contest, right? Who's going to catch the most fish? Well, how are you going to judge who wins this contest? There must be some way of counting the fish, right? And, you go out, you count, you catch the first fish, you've caught one fish, then you go out and catch another fish, now you've caught 2 fish. Your buddy catches one, now altogether you've caught 3 fish, and so on. These are natural numbers, also known as counting numbers, and also known as whole numbers. Okay, so these are all pretty much synonyms. Some people might quibble about if we should include the number 0 here. We're not going to include it for our purposes, but it's not a huge deal. These kinds of numbers are essentially the most natural kind of number that people would first invent thousands and tens of thousands of years ago in order to count, how many things do you have? How many fish do you have? How many people are in your family? In math, we have a special symbol we use for the natural numbers, and that is a stylized letter N. And it sort of has this double stroke through the diagonal, so N for natural numbers. What can we do with this? Well, we can count with them, right? What is counting, really? Counting is actually a kind of division, is it, right? Counting is actually a type of addition, right? So if you want to start with 1, you add another 1, well, you've counted up to 2. Right? You start with 2, you add another 1, now you're up to 3. You can do all kinds of addition. In fact, any 2 natural numbers, you can always add them together. You can add, 3 plus 2, and you'll get 5. You're always guaranteed to get a natural number out as a result. Any 2 natural numbers together, added together, guaranteed to give you a natural number as a result. And so that means we call this a kind of closure. We say that natural numbers are closed under addition. All right, you're guaranteed to get a natural number out. What about another kind of operation? Well, we could try subtraction, right? What if we do 3 minus 2? What does that equal? That equals 1. Great. That works, okay? What if we try 2 minus 3? Well, here we get a problem, don't we? Because imagine you start out with 2 fish, and now you take away 3 fish. How many fish do you have? Well, that doesn't make sense. How can I take away 3 fish if you're only starting with 2? You can't, right? And so for a very long time, people could not do this operation. It would just give them some kind of error, okay? Like undefined or something, right? Because how can you have less than nothing? It doesn't make sense. Now, if you've done math before, you know there is a way we can do this, but that requires us to invent a whole other class of numbers. Let's take a look at what that's going to be. The integers. These are going to be numbers like -2, -1, 0, 1, 2, and so on. So integers now take the set of natural numbers and expand them to include all of the negative numbers, all of the negative versions of the natural numbers, and also the number 0, right? That's an important innovation as well. And the symbol that we use in math for the integers is a stylized letter Z, okay? Again, with that double stroke through the diagonal. I believe the letter Z comes from the German word Zahlen, which essentially means like a number or a count. So integers here, by introducing negative numbers, allow us to do that operation we tried before. 2 minus 3, that's going to equal -1, and it works. And so now we can say that integers are closed under subtraction. You are guaranteed, if you subtract any 2 random integers, you will guaranteed to be getting an integer out as a result. Now let's talk about negative numbers here. What does that mean? Well, less than nothing is a hard thing to imagine, but negative numbers can represent a few things. They could represent maybe, how about direction? You could imagine positive numbers as maybe moving forwards and negative numbers moving backwards, right? So in that way, taking 2 steps forward and then 3 steps back, and I wind up 1 step behind where I started, right? That makes sense. So direction here makes sense for negative numbers. And we can also think about them as representing some kind of debt, right? Maybe that's another way to think about negative numbers. Like maybe so like a net worth. Like I caught 2 fish and then I owe you 3 fish. So altogether my net worth in fish is -1 fish, right? That's how much fish I'm worth. And in the future, when I catch more fish, I'll, give you an extra one and balance that out. So credit and debt is an important concept. So you can imagine, in history, back in time, when people started innovating with money, negative numbers would really come in handy. So integers are going to be closed under subtraction and, of course, addition. Now, what about other operations we could try here, right? Let's try multiplication, right? We could try 2 times 3, and that's going to equal 6. Well, that works. That's great. What about -2 times 3? Well, that's going to be -6, and that also works. These are all integers, right? Integer, integer, integer. Okay, so we can say that integers are going to be closed under multiplication. What about division? Okay, let's try 10 divided by 2. What's that? Well, that's going to be 5. Great, that works. What about 2 divided by 10? Well, that is a problem, okay? Because 2 divided by 10, well, that's something that's less than 1, but more than 0. And so this doesn't exist, right? Once again, we've reached the limit of our understanding with numbers, with integers. And so this is not closed, right? So integers are not closed under division. And instead, once again, we have to invent a new kind of number to deal with operations just like that. What's that going to be? We're going to call them rational numbers. Here we're going to include numbers like -1, 0, 1, but also 1/2 or 1/3 or many other examples. Essentially what we're saying is we're going to define a new kind of number, and that's going to be a ratio of integers, right? So look at 1/2, look at 1/3. These are all ratios of integers, 1 to 2, 1 to 3. Ratios can also be thought of as fractions or quotients, right? Some kind of division operation. So anytime you have a ratio or a fraction or a quotient of integers, you are essentially constructing a rational number. In math, we have a symbol for rational numbers, and that's going to be the letter Q. Now, Q sounds funny. You know, rational doesn't start with the letter Q, but we're going to save the letter R for something else. And Q here sort of represents the word quotient, right? So Q for quotient, which represents a fraction or a ratio for rational numbers. Okay. I want to look at all of these numbers because obviously 1/2 and 1/3 are ratios, right? But the number 1 doesn't seem to be a ratio. The number -1 doesn't seem to be a ratio of integers. What if I write down a number like this? How about the number 5? Okay, is the number 5 a rational number? Is this a ratio of integers? Well, at first glance, it just seems like an integer all by itself. How can we make this into a ratio? You can imagine this as the number 5/1. Right? That's the same. And now suddenly we've represented the number 5 as a ratio of 2 integers. We could also represent this number as, say, 10/2. Right? That's also now a ratio of 2 integers, and it's equivalent to 5/1 or 5. So what this is showing us is that there's many ways to represent the same rational number. Every rational number is going to have many, many representations. In fact, an infinite number of representations, right? Like this could be 20/4 or whatever you want. So this is one way we can see that all integers are also rational numbers, because you can always just take an integer by itself and put it over 1, and you've made a ratio or a fraction or a quotient, right? Let me throw out a few other ratios here. So how about the ratio 1/2 and 3/4? Okay, so if you were to type 1 divided by 2 in a calculator, you would get a decimal, right? And so this would be the decimal 0.5. And 3/4, that would be the decimal 0.75. So what this is also telling us is that every rational number can be represented as either a ratio of integers, as a fraction, or as a decimal, right? There's 2 ways to represent every rational number. And all of these decimals, and I guess you could call 5, right? 5.0, right? 5 is also a decimal. All of these are what we call terminating decimals, because they end after some number of digits. I guess you could write 0000 forever if you wanted to, but that's not really meaningful, right? The decimal itself, it ends. There's a finite number of digits in that decimal that completely represent its value. There are other rational numbers that are a little bit different. For example, the number 1/3, or how about 2/11, or how about 1/13. Okay, so if you were to type 1/3 in a calculator, you would get a big long number, wouldn't you? Let's try it out. 1 divided by 3 is 0.333333. And these 3's, they keep on going, right? If you actually do the long division, you're going to find that these 3's, they never stop. So we can write this as something like 0.333 ... going on forever. But there's a shorthand way to write this, and we can write this as 0.3 with a bar over it. So that indicates the 3 continues on repeating forever. What about 2 over 11? What do we get there? Well, let's try this. So 2 divided by 11, that's going to be 0.18181818. So you can see another 0.18 repeating, another infinite repeating decimal. And let's try 1/13. All right, 1 over 13. This one's longer, but it's 0.076923. 076923, repeating, right? So 0.07693 repeating, okay? And so here we have another decimal form that is this kind of infinite repeating decimal. And so these are going to be non-terminating decimals, but they're going to be called, they're some kind of infinite decimal here. So that's sort of an interesting property that we're discovering. Rational numbers are a ratio or a fraction of integers, but every ratio or fraction of integers can also be represented as a decimal. And essentially, there's 2 kinds of decimals that we can get. We're going to get either terminating or finite decimals or infinite but repeating decimals. So anytime you see a decimal that either ends or it continues on with some repeating unit, you know you're going to have a rational number, and that decimal could then also be represented as a ratio or a fraction of integers. Now, I do want to talk about sort of filling in the gaps between numbers. So for example, let's say over here we have the number 1, and over here we have the number 2. What I want to say is that there is a big range between the number 1 and the number 2. And inside here, in between, there's going to be a lot of rational numbers, right? So for example, in here, you must have the number 1.5 somewhere. And over here, maybe you've got the number 1.4, right? And in between 1.4 and 1.5, well, maybe over here you're going to have 1.45, right? And maybe over here you'll have 1.42, right? And you can split this gap into finer and finer pieces. 1.421, 1.422. You can keep going as much as you want, and as long as you have a finite decimal or a decimal that has some infinite but repeating chunk, you're going to have a rational number. And so it seems like we've found all the numbers, right? Like I can divide this up so as fine as I want, it seems, and I'm going to have a rational number there. But it turns out that's not correct. It turns out that there are going to be gaps inside here, in between the rational numbers, that the rational numbers can never quite fill. And I want to illustrate how we get there. So let's say I want to draw a, let's draw a square. Okay, so here's a square. And let's say I want to find the area of this square. If I tell you the length is 5, well, the area of this square must be 25, right? So 5 meters by 5 meters, the area must be 25 square meters. And we know that's true because the area of a square is going to be equal to the length of the side squared, right? So that's fine, that's easy. What if I take a copy of this square here, and I tell you that the area of this square is 2 square meters? That's possible, right? It's possible to have a 2 square meter square. That's fine. Well, what's the length of this side going to be? Well, it must be a number that multiplied by itself is 2. And that number must be then the square root of 2, right? The square root of 2, because the square root of 2 squared equals 2, okay? Now, the square root of 2 is an interesting number because if you put this into a calculator, you're going to find that the square root of 2 is 1.414213, etc., right? And this decimal actually never ends. It goes on forever. And also, it never repeats. Now, it turns out that means this is not a rational number. So this number here is equal to the square root of 2, but it is not a rational number, because there is no way for me to represent this number as a ratio of integers. And you kind of have to trust me here. I'm going to do another lesson where I demonstrate a little bit better why that's true, but I can't do it. So this is not a rational number, and that means we need to invent another new kind of number to describe what the square root of 2 is. Surprise, surprise, that's going to be the irrational numbers. So what are irrational numbers? Well, basically exactly what we just said they were. They are infinite but non-repeating decimals. They keep going on forever, but they never repeat. And so these will include numbers like the square root of 2, the square root of 3, but also some very special numbers like pi or e. And there's actually no special symbol here for the irrational numbers. But here's where things get a little bit interesting, because pi is a very special number, right? Imagine you have a circle. Draw that a bit better. And you've got a diameter of the circle, right? So let's call this diameter d, and the length around the circle, right? This circumference, well, we'll call that c. It turns out the ratio of the circumference over the diameter, well, that is pi, right? And pi is, 3.14159, and it keeps on going forever. So we can find this ratio when we go out and investigate things in the world. So this kind of maybe gives some credence to the guys who think that numbers are things that we discover, right? Because we find this kind of ratio of pi all over the place, not just with circles, but with lots of things. Doesn't quite convince me, but maybe it convinces you. So this is going to be the irrational numbers then. And if you take the irrational numbers and combine them with the rational numbers, what do you get? Well, now we finally get the real numbers. The real numbers then are going to include things like -1, 0, 1, 1/2, but also numbers like the square root of 2 or pi, right? So now it almost seems like we've got all the numbers. And in a certain sense, we kind of do, but also not really, because people are smart and inventive, and we can always create new kinds of numbers. The real numbers do have a symbol, and we're going to use the letter R, the stylized R, right? So we saved it for the real numbers. We didn't waste it on the rational numbers. Now, I did say that the irrational numbers did not really have a symbol, but sometimes you might see them represented as sort of the real numbers without the rational numbers. That sort of leaves the irrational numbers left. So I guess that kind of makes sense. So there we go. We finally got to the real numbers. The real numbers essentially are just going to be the rational plus the irrational numbers altogether. So the set of all of those numbers. And that way we kind of fill in all of the gaps between any two integers, essentially. Let me put it all together for you. Okay, so we started out looking at the set of natural numbers, right? Numbers like 1, 2, 3, 4. After that, what we did is we looked at the integers, right? So the integers included the natural numbers, but also included numbers like the negative numbers, right? After that, what did we do? Well, we looked at the rational numbers. So now we were able to talk about numbers that are in between the integers, ratios of integers. And after that, we looked at the irrational numbers, which was not a superset of these other ones. They kind of stood here by themselves, their own little group. And if you put them all together, what do we get? Well, now finally we get the real numbers. And that is where we're going to end for today. Okay, so hopefully that helped you understand what we mean when we talk about real numbers. And in the rest of Precalculus, we're mostly going to be working with real numbers. All right, I'll see you for our next lesson where we talk a little bit more about properties of real numbers.